Now we know how to differentiate our exponential functions. Let's look at it with rates of change questions. Very common one is this idea of growth and decay. And it starts with a very, very simple assumption that growth and decay is basically proportional to the population that you have. So the idea is obviously the more people you have, then the more people that will be born and the more people that will die, basically proportional. So in other words, the rate of change of population with respect to time would be some constant times the population. It's directly proportional. Now that is, as I say, a very simple model of growth and decay. Also, radioactive material, that also has this exponential growth and decay idea. The solution to this particular differential equation would be something like this. So P would equal some constant times e to the kt. Now once we've looked at integration, we can go and prove that. But at this stage of the game, well, let's do an example to show you the sort of question we might get. And this one comes from the 2015 HSC. The amount of caffeine in the body decreases according to, and there's the differential equation, to C to T is negative 0.14. So decreasing, so we're expecting a negative rate, 0.14 C. C is in milligrams, time is in hours. And so basically they say, we'll show this is a solution. So we don't actually have to do any integration to solve the equation itself. We can simply do a substitution and see if it works. The C is a e to the minus 0.14 t. Well, let's find out what its derivative is. And what we saw was we differentiate the power for an exponential. That's just a linear function. So I'll get negative 0.14 a e to the minus 0.14 t. Well, yes, that is minus 0.14 times what they told me C was. So it does satisfy that particular equation. When T equals 0, so the initial amount of caffeine in the body, we've got 130 milligrams, find the value of A. When T equals 0, C is 130, substitute it into our formula, and of course e to the power of 0 is 1. So that constant, what that's telling me is that constant actually turns out to be whatever the initial value is going to be, in this case 130 milligrams. Alright, how much after 7 hours then? Substitute in T equals 7. And rounding off to one decimal place, we've got 48.8 milligrams of caffeine. It really is, once we've got our equations, they really are just substitution questions. Plug a number in, what's the answer we get? What's the time taken for the amount of caffeine to halve? Right, well, half would be 65 milligrams. Substitute that one in, but now we've got this exponential equation to solve. Undo the exponential, do the inverse, which of course is our natural logarithm. I'll pause there. This log of a half. You might have seen it when you have dealt with radioactivity. Do they still do that in physics and chem? Radioactive growth and decay? They wouldn't have done it via calculus, I guess, but their formula for half-life would probably be something like this. Well, basically that's where it's coming from. That's why we get log of a half. So R1, it's going to be minus 1 over 0.14, the log of a half, and there we go. So about 5 hours, 4.95, about 5 hours, the caffeine will halve. So 11F, looking at these growth and decay questions.